Welcome back to Pachehra Talks. And today, in Artificial Intelligence series, we are going to understand and explore the learning models. Yes, in the previous video, we just introduced ourselves with the learning models, which are actually the algorithms and techniques that enables any computers or machine to learn from data. So this is what actually working behind the artificial intelligence. So we in the previous video we saw there were uh, these many learning models which is commonly used. So we know already what is learning models. Learning models refer to algorithms, or we can just make a point here: algorithms and techniques that enables any machine or computer to learn from data and improve their performance over time without being explicitly programmed for every task. So it will start learning by itself, right? So that's what the learning model is, and I mis- misspelled it, but you know what it stands for: algorithms, right? So these models are the core of AI or machine learning, which is a subset of AI focused on the development of systems that can learn from and make decisions based on data. All these fields are based on data. And understanding different types of learning model is crucial for applying AI to a broad range of problems, because we build the AI once we have the problem statement to solve it that we already covered in the previous video. So let's start with understanding these models that we have right here one by one. So the very first is supervised. All right, so what is supervised learning? Well, as the name says, which hints supervision, right? Or which could be like, we know what it is, right? And what we know, it's the data. We know the data and on which we are training the model. Or in other words, supervised learning involves training a model on a labeled data set. Labeled data set, which means that each example in the training data is paired with the correct output, which means we already know the data. For example, a very good and simple example, whether an email is a spam or not a spam. So we are training on a data or which we already know whether it's a spam or it's not a spam. So the model learns to predict the output from the input data. After training, model can apply what it has learned to new or unseen or fresh data which is not labeled, right? So we are training this data under the supervision of labeled data set. That's why it is called supervised learning. And it has two categories. Okay, let me put this one here. Come on. And it has two types of categories that we need to understand. The very first is classification. Classification. And the other one is regression. Regression. All right. Now, as the name says, classification, it's classifying. But what exactly it is classifying? It's predicting the categories. Classification of the categories. Classification is used when output variable is a category. Let's put the same example here: spam or not a spam in an email filtering system, or you could say animals, but categorizing into cat, dog, bird, the image recognition task that would fall under the classification. But if we talk about the regression, regression is like predicting continuous values, which means numerical values. Regression is used when the output variable is a real or continuous value, such as temperature, prices, or height. A very good example is consider a real estate application that predicts the price of a house based on a features like location, size, and the number of bedrooms. So continuous value, numerical value. You train your model on a data set where each house's features are known along with its selling price. The model learns the relationship between the features and the selling price. For a new house, given its features, the model can predict its selling price based on the patterns it learned during the training. So that's a regression. So it's a classification and it's a regression. And the main difference between these two is main difference is in the output, right? That's what we said. That's how we explained it. Classification predicts the discrete categories, right? Labels. And whereas regression predicts the continuous quantities, numerical values, right? So that's how they different with each other, but both are the supervised learning. They fall under the supervised learning. All right, very nice. What is the next one? So we are done with the this one, supervised one. Now it's time to understand the unsupervised. Okay, let's put it here. Unsupervised. Unsupervised. All right. What is unsupervised learning? Well, it's exactly opposite of the supervised. In supervised, we had the label data, but here we do not have any uh, no labels or data set is not explored or known. The system tries to learn from the data. What exactly it's learning? It's learning patterns. Okay, it's learning structure from the data by itself because that's how the model is built. The goal is to model the underlying structure or distribution in the data to learn more about the data. Right. So what we are doing here, what the unsupervised learning is doing, we are not classifying anything or regressionized anything. We are just trying to learn something out of the data because data has no labels. So what we'll see the patterns. All right. Our learning will see the structure of the data. Let's take an example of like grouping data points into clusters of similar items. Clustering involves grouping a set of objects in such a way that objects in the same group called a cluster are more similar to each other than those in the other groups. Right. So that is one of the category of unsupervised learning where as per the patterns and the structure we form a cluster. Imagine you have a library and you want to organize books in a way that similar books are kept together, but you're not exactly sure the categories beforehand. So what do? You decide to use clustering. The algorithm scans through all books, analyzing topics, writing styles, and other features. It might end up grouping books into clusters such as fiction, non-fiction, science, literature, and so on, based on the similarities it finds, the patterns, the structure it finds. Each cluster represents a category of books that are similar in content or style. So one of the unsupervised learning is clustering. So it just form a group, a cluster of those similar items. And there is one more type which is dimensionality reduction. Dimensionality reduction. Okay. It seems little odd, but you'll find it interesting because reducing the number of random variables to consider for simplifying data visualization. Because every data has so many features, values, a lot of things, but you may not need all those things. That's what it is doing. It is reducing the number of random variables to consider for simplifying data visualization. And this dr not exactly dr but dimensionality reduction is the process of reducing the number of random variables under consideration because it's not impacting the value directly by obtaining set of principal variables, right? Because it's not so. We have to consider only those values. It will help us to consider only those values which are actually affecting the results. It's often used to simplify data, reduce noise. That's the right thing. Reduce noise and improve the efficiency of the algorithm. So let's take a simple example of a grocery store. Let's Grocery store chain that collects detailed data on its sales. Now, including day of the week, time of the day, types of product sold, payment method, and many more features are there. While analyzing this data to understand sales patterns, they find it challenging to work with because of the sheer number of variables. So, using this dimensionality reduction, they can simplify the data to focus on just a few important factors like day of the week and types of products sold that most significantly affect sales. This is not only makes analysis easier but also helps in visualizing trends and patterns more clearly, as they can now plot data in 2 or 3 dimensions. That's why it's dimensionality reduction, 2 or 3 dimensions. So dimension and reduction of random variables are the keywords for this one. For clustering, what was it doing? It was grouping similar items, right? We took the example of library here just for the summarizing, and here we took the example of grocery store. All right. Now, clustering aims to discover inherent groupings in the data, whereas dimensional reduction seeks to simplify the data by reducing its features to the most relevant ones. And clustering and dimensionality are powerful techniques in unsupervised learning. That's what we are learning. These are falling under unsupervised learning for uncovering hidden patterns in data, whether by grouping similar items together or by simplifying the data into most informative features. Right? So that is unsupervised learning. That is unsupervised learning. All right. So let me just make it little clear. It has two, and these things we have gone through: supervised and unsupervised. All right. So I think I should open another one. All right. Where we can start with the third type, which is semi-supervised. Now your mind must have started wondering in a right direction, hopefully, because it's semi-supervised, which makes its point visible, right? It's neither unsupervised nor supervised. It's semi-supervised. Means learning falls between supervised and unsupervised learning. It uses both labeled, labeled and unlabeled data. So it uses both the data for training. This approach is useful when acquiring fully labeled data set is expensive. You see, these kind of technology is all data based, right? And sometimes it's not cheap or enough to, or like get the enough data to build the most efficient appropriate model. So in that situation, we can simply work as a semi supervised learning. So how it helps? They are this is there is one way is combines methods from both supervised and unsupervised learning, right? So often used to improve the learning accuracy with limited labeled data. So what is the plan? The both kind of data is there, but first what it starts learning accuracy with the limited labeled data first. Okay. Semi supervised learning is a machine learning approach that involves using a small amount of labeled data alongside a large amount of unlabeled data during training. Right. So we have labeled data, we have unlabeled data. It will start learning on the labeled data and try to uh, correct itself on the unlabeled data. The idea is to improve the learning accuracy. That's the idea. Learning accuracy. And how it can accurate its learning? By learning on the labeled data and applying on the unlabeled data and checking the result. Right. uh, which in turn enhances the performance on the labeled portion of the data, right? So the wonderful example that we can take for this one is, imagine you are developing a system to sort customer reviews into two categories, positive and negative. You have a small number of reviews that have been carefully labeled as positive or negative. Let's suppose, like, we have small labeled data, but you also have a much larger cache of reviews that hasn't been labeled. So you can consider that as unlabeled or unsupervised learning or unlabeled data, right? So in a semi-supervised learning approach, you might first use the labeled reviews to train a basic classification model, right? What are doing? We are simply training on labeled data, reviews, to train a basic classification model. You remember the classification? They was falling under supervised learning, classification and regression. So that's what we are doing here. Basic classification model. Then you use this model to make predictions. Now what we're doing? Predictions on the unlabeled data. See how we are, how smartly this is working, because we cannot acquire all the labeled data. That's how we are doing. We are just training it to the basic classification model, and by that we are utilizing classifications feature and predicting the unlabeled data. Some of these predictions will be made with high confidence. You can add these confidently predicted reviews into your training set as if they were labeled from the start. This process enriches your training data, allowing your model to learn more about the nuance of what makes a review positive or negative based on a broader set of examples than just the initial label data. Right? So that's how it works. And it has, again, it has two common categories, which is self training, and there is one more which is called co training. Now you can guess with the name, of course. Now, what is self-training? Self-training model is initially trained with a small amount of labeled data. It then uses this initial model to label the unlabeled data. The most confidently predicted labels are added in the training set, and the model is retrained with this augmented data set. The example that we took of positive and negative reviews. Now, co-training involves splitting the feature set into two subsets, training two separate classifiers. Each classifier then labels unlabeled instance of the other to learn from, effectively teaching each other from unlabeled data focused on different views of the data. See how brilliant it is. It's teaching itself, it's teaching in two groups, teaching one and another. That's how it is working. So that is semi supervised data. So it has these two types of training, self and co-training. Now, what are the key benefits of this? Well, semi-supervised learning can significantly reduce the need for labeled data, which is often expensive or time consuming to obtain. That is the reason people use this, not because they wanted to have fun, because we do not have the uh, exact data because of the obvious reasons, right? So by utilizing both labeled and unlabeled data, the model can achieve higher accuracy, especially in cases where the labeled data is not fully representative of the entire data distribution. So that is our third category. Now fourth one is really interesting, and we already have AI working on this one, like so many, but the one which is most in use is reinforcement learning. All right. So reinforcement learning, as per the name, somebody is reinforcing to learn in a positive way, is a type of learning where an agent learns. So what is happen? Agent learns to make decisions by performing actions. So agent learns to make decisions by performing actions in an environment to achieve some objectives. Okay, we have to write the decision. What agent is learning? Agent learning decisions. Okay, by performing actions in an environment to achieve some objectives. Now you will understand why I'm writing this, because all these things will help us to learn, because reinforcement learning. Just bear with me. We'll start connecting the dots, and you will be happy. If you already know, then you must be smiling. So it learns from the consequences of its actions, just like humans. Like, rather than from explicit training data, and adjust its strategy to maximize the cumulative reward. All right, decision making. Learning policies for decision making is a wonderful example of reinforcement learning. And this example I'm going to give you right now will help you clarify everything what is happening here. Or before we start the example, I'll tell you, it is like, if you are taking a right decision, somebody is going to appreciate it. If you are taking a wrong decision, somebody is going to scold you. But it's a machine, so we maybe give the +1 or -1, like reward. And you know all right, so let's take an example. Imagine we have a robot whose goal is to navigate through a maze, all right, to find a piece of cheese. All right, this is a mouse robot. The maze is the environment, and the robot is the agent in this scenario, right? Because these things are working in an environment, of course. Environment. Now we have an agent and we have an environment. The robot can move up and down, left and right, and it has learned the best path to the cheese. That is the objective. And whatever it's doing is the action. Which is the right action is the decision, right? So that's how they are preparing these things. All right. So let's take a step one, which is exploration in this learning, where the robot moves randomly, because the robot doesn't know anything. It just moves randomly because it has no experience. It might hit walls, take longer routes, or even move in circles. Now, action is direction. I told you, like, it can move. Now, what is reward here? Maybe getting closer to the cheese increases its reward, while hitting a wall or moving away from the cheese results in the penalty, maybe negative reward, which it is this model already has, where it can see the negative point and the positive point. So how it is getting these point? Like feedback. Like even in the chat GPT, if you see, there is an option of feedback. If you don't like it, you should reply like, we don't like it, that's how it should be. Even that is learning by itself. So each time the robot moves, it receives feedback in the form of rewards or penalties. Hitting a wall might give -1 point. Moving one step closer to the cheese might give +1 point. The robot uses this feedback to update its strategy and trying to maximize its total reward. That's how it is functioned. What it needs to do, it needs to increase the reward, right? And how it will increase the reward? By updating the strategy. It's moving here and there, and it's getting the point. Whenever it's getting the +point, it will keep that in mind and prepare its strategy accordingly, right? So how it will develop this one? By over many attempts, the robot starts identifying which action lead to higher rewards. It learns, for example, that moving towards the cheese is good and hitting wall is bad, in a simple way. The robot develops a strategy that maximizes its reward, effectively learning the best path to the cheese. Right now, it knows how it's done. But that's not it, because we are in a realm of continuous learning and optimization, right? So as the robot explores the maze and receives rewards, it refines its strategy to find the quickest path to the cheese. It learns to anticipate the consequences of its actions before making them, improving its decision making process to achieve its goal more efficiently. So that's how this reinforcement learning works. And this is an simple example that we took. That's these things actually happens, like they have agent, they have decision, they have actions, object, environment. On the basis of these, they have what? They have reward or punishment strategy, whatever, positive or negative point, right? So that's what the key concepts of reinforcement learning. So this example illustrates the basics of reinforcement learning. An agent interacts with its environment by taking actions and learning from rewards or penalties it receives. Over time, it develops a policy to maximize its cumulative reward, improving its decision-making ability to achieve its goal. Reinforcement learning is widely used in various applications, from game playing and robotics to optimization problems and autonomous vehicles, where agents learn to make a sequence of decisions to achieve their objectives. Very nice. Now, another one that we are learning is the self-supervised. Now, any guesses with the self-supervised, semi-supervised? We understand reinforcement gives something, and similarly, self-supervised is giving out something, which simply means a type of unsupervised learning where the data provides supervision. It involves creating a predictive task from the input data itself, using part of the data to predict another part. It's particularly useful for learning representation from large amounts of unlabeled data. You'll get it once I'll start with some example. Let's take in feature learning, like learning useful representation of data without explicit labels. Uh, that's how actually self-supervised learning works. Okay, so it is type of unsupervised learning where data provides supervision. Data does not are not labeled like in supervised, or uh, not giving anything like unsupervised, but it's giving something. It's providing supervision. Okay, let's take an example, then I could hit it particularly the way I want to. So imagine you have thousands of photos on your smartphone and you want to organize them without going through each one manually. You decide to develop a smart photo organization app that can automatically group photos by similar features such as landscapes, people, animals, or events. However, you don't have any labels for these photos that specify their content. What will you do? Well, to tackle this problem, the app uses a self supervised learning approach. It generates a pre-text task by automatically creating puzzles from your photos. Okay, now it's learning from the data itself. Data is the supervision. For instance, it might divide each photo into several pieces and then mix the pieces up, asking the model to put them back together. So what will happen during that process? Learning will happen. Learning. Let's see. All right, the step one would be understanding basic features. To solve these puzzles, the model starts learning basic visual features such as edges, texture, color. For example, it learns to match the blue pieces representing the sky or the green pieces for grass. Then it will do advanced learning. As the model gets better at solving these puzzles, it starts to recognize more complex patterns such as distinction between faces and objects, or the typical features of a landscape versus a cityscape. Then, well, apply the learned features. For example, clustering the photos. So, armed with the features learned from the pretext task, the model can now group photos with similar features together. It can identify and cluster all beach photos by recognizing the common patterns of sand and water, or group all birthday party photos by detecting features like balloons, cakes, and groups of people smiling. So, now what? Now facilitating the search and organization. That's the objective, right? So you can now search your photo library with the terms like beach, birthday, or pets, even though you never labeled any photos. The app uses the features learned through the self-supervised task to understand the categorize your photos automatically. So what it does, it start with the pretext task, right? Start with the pretext task. What was those? Self-supervised learning approach. That's what it is. It generates a pre-text task by creating puzzles of your photo so that you start going and resolving the puzzle and start learning. Then learning, then advanced learning, and then it start clustering the photos, and finally facilitating search. That's how it completes the self-supervised learning. So, in this scenario, the self supervised learning model learned valuable features about the content of the photos by solving a self generated puzzle task. This approach enabled the model to organize and categorize the photos based on their visual content without needing any manual labeling. It's a practical example of how self supervised learning facilitates feature learning, making it possible to extract meaningful information from unlabeled data, which can then be used for various applications, including simplifying everyday tasks like photo organization, because now it's trained. All right, interesting. Let's see the another one, which is a transfer learning. Okay, what are we transferring now? Oh, yeah, that's the keyword right here, transfer. Transferring involves taking a pre-trained model on a large data set and fine tune it for a different but related task. Very nice. So it's taking one of the trained and using it on a different task or related task. This approach is beneficial for tasks where label data is scarce, as it allows leveraging knowledge gained from one task to improve the performance on another. Right? Existing pre-trained model for related task. So we are not spending too much time in training the model, but we are utilizing what all it has trained to work on a related uh, task. So let's take an example to understand it further. Let's take an example of imagine you have developed an AI model that is excellent at recognizing different types of fruits in images. Okay, it can distinguish apples from oranges, bananas from grapes, and so on. This model has been trained on a vast data set for fruit images, learning various features like shapes, colors, and texture. All right, pre-trained model. It is pre-trained model that we are talking about, but it's on fruit images. But it is learning on something, learning on like shapes and colors and texture. It knows, the model knows these things, but it answers only in the fruits. So the original task is fruit recognition. The model has learned to identify and classify fruits. But what we want to leverage this and would like to identify, let's say, vegetables. Okay, now we want to recognize vegetable instead. Let's say you have some vegetable images but not nearly as many as you had for fruit, and you want to avoid the time and resource cost for training a new model from scratch. That's the whole purpose, right? So what's the new task? Vegetable recognition. So what we'll do, the step one, we'll use the pre-trained fruit model. We'll start with the model we already have, like trained model on fruits. This model has already learned a lot about general visual features that can be relevant for recognizing vegetables, such as colors and texture. We are okay till now. Now, what we need to do, we just need to fine tune it. We need to give the information of vegetables, right? So we slightly adjust or fine tune the model's weights and biases primarily in the last few layers so it can learn about vegetables based on the features it learned from fruits. This might involve replacing the final classification layer with a new one tailored to vegetable categories and training the model on your vegetable dataset. So, feature extraction could be another approach is to use the pre-trained fruit model as a fixed feature extractor. You remove the top layer, the one that makes the final fruit prediction, feed in vegetable images, and use the output as input to a new model that learns to classify vegetables. Okay, that this is called feature extraction. Now, training on vegetable images. You train the adapted model on your smaller data set of vegetable images because the model has been pre-trained on a large data set of fruits. It requires less data and fewer computational resources to learn the new task of vegetable recognition. Right. So this example, in conclusion, this example, I know it's little tough one, but if you just give it a time, it will sink in. This example, let me try to conclude it. It might help. Uh, this example illustrates the essence of model adaptation in transfer learning. Leveraging knowledge like features and patterns from one domain, which was fruits, to improve performance in another domain, which was vegetables. It's a powerful technique in machine learning, allowing for more efficient use of data, faster training times, and improved performance, especially when dealing with related but distinct tasks. Right? So that's what is transfer learning. We are transfer learning and model adaptation that we talked about. Adapting a model trained on one task to perform on another task. All right, it was little exhausting. Only the last one is left. Just stay with me, which is federated learning. Any guesses? As the name says, federated learning, something's related to privacy, hands down. So, federated learning is a distributed approach where the model is trained across multiple devices or servers holding local data samples without exchanging them. Okay. All right. So, this method is useful for improving privacy and reducing the need to centralize the data. All right. We need to dig it deeper to make it sense to us, right? So, let's do the distributed training. Training models across multiple devices while keeping data localized. All right. Uh, let's take an example. That is the best way to understand these things. Imagine a tech company wants to improve the next word prediction feature of its smartphone. All right, so typically this would involve collecting a vast amount of typing data from users, sending it back to the company's server, and training a predictive model on the centralized data. However, this approach raises significant privacy concerns and involves transferring large amounts of data, which is not an easy task. Right, so what is the goal here? Improve the next word prediction without compromising user privacy or transferring large data set to a central server. Obviously, we don't want to do that. And what is the answer? Local model training. That is the answer. So what we'll do? Well, each smartphone has the keyboard app installed, which includes a basic predictive text model. That's all we know. So, as individual users type messages on their phones, each device's version of the model learns from the user's typing habits, updating itself to better predict the next word based on the unique data it encounters. These updates are made without sending the actual data out of the device. Well, you must have experienced this, right? So, periodically, the smartphone sends just their model updates, not the text data itself, to a central server. This could include changes to the model's parameters that reflect the learning from each user's data. The central server aggregates these updates from many smartphones to improve the global predictive text model. This aggression not aggression, aggregation might involve averaging the updates or applying more complex algorithm to combine the learning effectively. So what we need to do? We need to update the global model now. After aggregating the updates, the central server sends the improved global model back to all participating smartphones. How smart it is. So each smartphone then updates its local predictive text model with the global improvements. This cycle can repeat continuously, enhancing the model's accuracy and relevance for each user because we believe in continuous improvement. So, in this federated learning, uh, uh, let's talk the example so that it will start more sense. Distributed training allows for the collaborative improvement of a next word prediction model across many smartphones without compromising user privacy. Each device contributes to the model's learning process based on its local data, and through aggregation all users benefit from a continually improving service. This approach exemplifies how federated learning leverages distributed data sources to enhance machine learning models while addressing key challenges like privacy and data security. So, these learning models represent the diverse strategies AI systems use to understand and make predictions about the world. The choice of learning model depends on the nature of the task, the type and the amount of data available, and the specific goals of the AI application. Each type of learning model offers unique advantages and is suited to particular kinds of problems and data set in the vast and evolving field of AI. I hope it was informative. I know it is a little heavy, but you need to watch a couple of times to make sense what exactly I was trying to highlight here. But I hope it was helpful. Well, thank you for watching, and you guys have a wonderful day.